So you're welcome once again to today's section. We'll be looking at Module 11, which has to do with network communication devices. Here in this module, we're going to have some takeaways, which actually define the milestone of the course. One, we're going to look at how network devices enable network communication. And we're also going to look at how wireless devices enable network communication. So these are two distinct entities we're going to discuss today. One is on the network and two is on the wireless. And I think this also helps us to look at the security issues around these two border areas. So let's go take a deep dive into the section properly. First is network devices. We all know when we said network devices, we begin to have begin to recall devices like routers, switches, hubs, bridges, and all that. So quickly, we look at under network communication devices, we look at end devices. When you say end devices, you're looking at the recipient devices. So you have devices at the end node, which could be your printers, your IP phones, could be your computer, and any other devices. They are all referred to as end devices. So the most familiar network devices are end devices, and end device is either the source or destination of a message transmitted. So you can have it from the source, you can have it at the destination. Recall, you have a full duplex in this case where you receive and transmit. So the source and the destination. And then you also have a channel in between. So to distinguish one end device from another, each end device is on a network. You need an address to be able to distinguish one from the other. If you look at the topology on the right-hand side, you agree with me that you have the PC at one end of the LAN, and then you have PCs on the other end of the LAN. So the only way to distinguish between these two entities here is the help of IP addresses, of which they will never be the same considering their location. So when an end device initiates communication, it uses the address of the destination end device to specify where to deliver the message. So actually data originates with an end device, flows through the network, and arrives at an end device. So you can see in between the two, you have an intermediary device, which in this case, we call it inter-network, and that's your router in this case. So you have a video to actually play to help buttress this information, which has to do with the characteristics of the end devices, and then the characteristics of the internet, and among others, and then the intermediary devices. Now, all that gives us a clear view of what this end device is all about. So here we can see an example of network communication device, which is routers. Routers are actually more on layer 3. As you can see, you have routers on the layer 3 of the OSI model. And the routers are used to interconnect remote sites. For those of us that are actually new in this domain, the routers are also like your LAN. It keeps all the IP addresses, your IP table. They make intelligent decisions when it comes to routing of your packet. They also do what are called best path selection. Routers have IP table, and in this IP table, it has different protocols in which it uses to actually send in this packet out of the network. And there are several routing protocols which the router obeys. And these could happen in the form of static routes, it could be dynamic routes, and all that. So we're going to look at some of them in this module and see how the routers are able to carry out communication in terms of taking packets from one point to the other. So the routing process is using network routing tables, like I said, protocols, and algorithms to determine the most efficient path for forwarding an IP packet. So these algorithms that the router uses comes in different protocols. So you could have what we call the RIP, which is Routing Information Protocol. That actually could be in RIP version 1. We also have RIP version 2. We have OSPF, Open Shortest Path First. We have ERGRP, which is a Enhanced Interior Gateway Routing Protocol. These are inbuilt algorithms, more or less like metrics that helps the router to make some intelligence in terms of routing of packets or forwarding of an IP packet. So routers gather routing information and update other routers about changes in the network, because routers are interconnected. You connect one router to the other, just like you can see in the topology to your right. You also agree with me here that because they're interconnected and they form what we call neighbors. Just as long as they are connected, they have to know each other. And if they know each other, they will know each other through what we call the IP tables. So that means they will share information. And the information they will share is about existing connections on each of these routers. For instance, this is a segment here. This router here has connections to all these systems, and all the systems are zooming actually configure the network, so they have some kind of IP addresses, and these IP addresses will form an IP table in this router. Same to this router, same to this router as well. So at the end of the day, you realize that these separate routers have their individual IP addresses based on their LAN connection. And because they have that, they form what we call an IP table. And this IP table, because they are also connected to neighboring routers, they share information about this IP table to the other router. So that means on each of this router, once it synchronizes, you have the IP table of this router in the other router, and all the routers get to have the IP tables based on what we call exchange of hello packets in some of the routing protocols. So there are conditions or parameters that make router to update themselves, and sometimes in some of the algorithms they can update themselves after every 30 minutes, as the case may be. And then the reason why they do that is because they just want to have current information about what is happening in the neighboring routers. So routers gather routing information and update other routers about changes in the network. So when there's a change, for instance, there's a disconnection of one of the switches here that is actually connected to other systems, automatically the router here will make a change and said, oh, right now I don't have this set of guys connected to me, so I'm going to update myself. And once it updates itself, it also passes the same information about the changes to the neighboring routers. And that is how the other routers update themselves, and then information is maintained. So the next time the neighboring router is sending information, it just do what we call a lookup to its own routing table and knows where the destination device is, and then forward the IP packet. So routers have two primary functions, which you always remember. They do what we call path determination and packet forwarding. So to perform path determination, each router builds and maintains a routing table. So routers form what we call a routing table. And what is the command for you to check that? When you do show IP route will help you know about the routing, which is quite important. And then the routing table can be built manually and contain static routes, or can be built using a dynamic routing protocol. Like I said, the table of the router containing all the IP addresses can be statically or can be dynamic. So whichever way depends on what the administrator of that network chooses to use at every point in time. So packet forwarding is accomplished by actually using a switching function. And switching is the process used by a router to accept a packet on one interface and then actually forward it out of another interface. The router itself has different connections, as you can see here. The router could receive from this end and then forward it through the other end. So a primary aim of the switching function is to encapsulate packet in the appropriate data link frame type for the outgoing link. So after the router has actually determined the exit interface in which it's going to forward the IP packet using path determination, the router must encapsulate the packet into the data link frame of the outgoing interface. Reason because if it's connected to the Ethernet port, it has to encapsulate it to the other layer. Now, when a packet received from one network and destined for another network, the router performs the following three major steps, which is you always remember. One, it de-encapsulates the layer 2 frame header and trailer to expose the layer 3 packet. It's doing this when it's actually coming in from the layer 2. And then it examines the destination IP address of the packet to find the best path, in the routing table. Like we said, one of the strongest attributes of the router is that it does what we call best path selection. If the router finds a path to destination, it encapsulates the layer 3 packet into a new layer 2 frame, and for the frame out, exit the interface. So here, still on routers are shown in the figure. You can see the router here. In the figure here, R1, R2, R3 are all routers. IP4 addresses. So while Ethernet interfaces have layer 2, data link layer, the MAC addresses are shortened to simplify the illustration. So you know where the MAC addresses are. The MAC is actually connected to the system as each individual system from here, from the router here to the PC. So as packet travels from the source device to the destination device, the layer 3 IP addresses do not change, of course, as the layer 3 PDU does not change. So the layer 2 data link addresses change at every router on the path to the destination. So as the router is de-encapsulated and re-encapsulated in a new layer 2. Remember, there's this interconnection between layer 2 and layer 3. So it's either it is coming down from layer 3 to layer 2, or it's leaving layer 2 to layer 3. But whichever way it is, we're saying that as it travels from layer 3 to 2, of course, it has to be re-encapsulated into the new layer 2 frame, because in layer 2 you have the data PDU is actually a frame. So this is what you need to know here. And then packet forwarding decision processes. Now the router must determine how to encapsulate the packet and forward it out the correct ingress. Ingress is out, and then ingress is in. So the following steps describe the packet forwarding process shown in the figure. So here you can see that the data link frame with an encapsulated IP packet arrives on the ingress interface. Okay, so the router examines the destination IP address in the packet header, and then what does it do? It consults its IP routing table. So the first thing is that the router would first of all do a check, and examine to see, oh, where's the destination IP address? Okay, fine. From the routing table, I can see that. It has to consult its routing table. So the router will now find the longest matching prefix in the routing table. Remember, also the longest routing prefix, we're talking about the subnet landmarks here, which is whether it's a /26, whether it's a /27, whether it's a /28. So the router will find the longest matching prefix. The router will encapsulate the packet in a data link frame and then forward it out the ingress. And the decision could be a device connected to the network or a next hub router. It all depends on where it is connected to. So if there is no matching route entry, the packet is actually dropped. So packets will be dropped if it is not matched. And what is it matching? It's matching to this IP table to be sure that from its IP table is able to see the destination device. So still on network communication devices, packet forwarding decision process. So the three actions a router can perform with a packet after the best path is determined. Remember, the router will always use its algorithm, and the algorithm we're talking about is a routing concept or a routing protocol based on what is configured to work with either of the link state or distance vector routing protocols. We're saying that the router will have to make some decision after it have established the best path to take to reach the end device. It will forward the packet to a device on the directly connected network, and then forward the packet to a next hop router, which is a router next to it, and drop the packet. No matching, that does not match in the routing table. So it's one thing that the router has established a connection to the end devices, and the router will now have to send through the neighboring router or the directly connected router, or it will forward it to the next hop, which is like the next router. But also when it checks and see that, well, I've checked the routing table, there's no match, I can see the destination device, what we're saying is that the router will drop the packet. So forward the packet to device on the directly connected network. So these are very strong conditions. So if a route entry indicates that the ingress interface is directly connected to connected network, actually this means that the destination IP address of the packet will belong to a device on the directly connected network. So here we're saying that if that IP address that is connected directly means that the destination IP address, it actually means that it's connected directly to the network because of the IP address. So the packet can be forwarded directly to the destination device, an end device on an Ethernet LAN, which means the packet must be encapsulated in a frame Ethernet, encapsulated in an Ethernet frame. So what we actually mean here is that the packet can be forwarded directly from that router, considering the fact that it does actually match it to this IP table and is sure that that device exists in its local LAN. It has to do that through the main by actually encapsulating it into a frame. If you look at the connection from the Ethernet port, to encapsulate the packet in the Ethernet frame, the router needs to determine the destination MAC address that is associated with the destination IP address of the packet, meaning that it's sending it to the destination device. It actually needs to take into consideration the MAC address of the destination device. Okay, so packet forwarding processes. The process varies actually based on whether the packet is an IPv4 or an IPv6. Remember, we have two IP protocols, either 4 or version 6. So for the IPv4 packet, the router checks its app, which is the address resolution protocol table for destination IPv4 address. Remember, in the practical we did, it's going to actually resolve the MAC address to the destination IP address. So if there is no match, the router sends an app request, and the destination device will return an app. So the app is what the router uses, to check on the connecting device so that it can have its MAC and IP addresses all registered, so the router can now forward the IPv4 packets in an Ethernet frame with the proper destination MAC address. For the IPv6, the router checks its neighbor cache for the destination IPv6 address and then an associated Ethernet MAC address. So if there is no match, the router sends an ICMP version 6, which is like sending an echo message, and the destination device will return with an ICMP version 6. Remember, the ICMP is the Internet control message protocol. It is MAC address. So the router can now forward the IPv6 packet in an internet frame with the proper destination MAC address. So let's look at forward the packet still on the next hop router. So if the route entry indicates that the destination IP address is on a remote network, this means that the destination IP address of the IP packet belongs to a device on network that is directly connected to it. So we've actually explained this before. We've given this condition that these are conditions that we must know that before the router forwards packet to its next hop, it has to do this check. So you can also do the check through the app, which is the address resolution protocol. It will do a check and see to learn about the table of the other router. Remember, it will always mark the IP address of the destination device. To also mark it up with the MAC address of the source. So remember also that it will drop the packet when it check its routing table and there's no match. Now, routing information. The routing table stores the following information. Remember, we said routers build routing tables, and these tables are actually in the memory. The router has a RAM, like you have a RAM in your local PC. So what is a RAM in your PC doing? It keeps information, it keeps content. So also the router has its own memory where it keeps its information. So the router stores the following information. One, the directly connected route based on directly connection routers. A remote route, that means routers that are not directly connected, but are connected outside their locations. So a routing table is a data file in RAM that is used to store route information, like I said, about directly connected and remote networks. So the routing table contains network or next hop associations. When we say next hop association, we're talking about routers that are connected on that particular link. So from here, you can see the routing information. You can see, you agree that the figure identifies the directly connected networks. Like you can see this, router 1 and router 2 directly connected. You can see router 1 having these two IP addresses, or what we call IP networks, in its routing table. And it also have this one because they're directly connected. So router 1 will have this IP network here, just like router 2 have same. So the destination network entries in the routing table can be added in several ways. One is through the local route interface. These are added when an interface is configured and active. And actually, two, directly connected interfaces. These are added to the routing table when an interface is configured and it is active. And true static. So it could either be local. So we're looking at how routers can actually exchange information, among other routers. So you could do it through the local route, could do it through directly connected interfaces, and then static route. This is a situation when the route is manually configured and the X interface is active to ensure the forwarding of IP packets. So dynamic routing protocols is added when the router protocols that dynamically learn about the network. So example of dynamic routing, ERGRP or OSP. Always note this. This is actually dynamic routing protocol. So one of the first dynamic routing protocols that ever existed is the RIP, which is the Routing Information Protocol, and RIP version 1. They were released in 1988. That was long ago. So the address needs of of larger networks, two advanced routing protocols, open shortest path, which is the OSPF, and the intermediate system to intermediate system were developed. So you can see after the RIP came the OSPF and the ISIS. So Cisco developed the interior gateway routing protocol, and then the enhanced interior gateway routing protocol, which also scale well in larger networks. So the border gateway routing protocol becomes still external. It's now used between internet service providers. So the following table classify the protocols, which are one. So when we talk about routing information or routing protocols, one, you need to know what the protocols are, and two, it's divided into two, interior and exterior. The interior is one distance vector and the link state, while the exterior is the path vector. So example of distance vector is your RIP, EGRP, and then for your link state is OSPF, ISIS, and then for your exterior, which is your path vector, is the BGP, which is the border gateway routing protocol. So here we look at the end-to-end packet forwarding. The primary responsibility of packet forwarding function is to encapsulate packets, that we know. And if you look at this diagram very well, playing the video, you will agree with me that in the first animation, PC1 will send a packet to PC2. You can see where PC2 is located. Note that if an app entry does not exist in the app table, that's for the default gateway of 192.168.1.1, what happened? The router R1 then return an app reply. So it will always, first of all, send an app request. The reason why I send an app request is to learn about the neighboring connection, and so that you can create a cache. So this is a temporary memory where it keeps this record. So R1 will forward the packet to PC once that's learned about, when it's sure that it's actually in the routing table. So R1 now forwards the packet to PC2 because the exit interface is an Ethernet network. R1 must resolve the next hop. So R1 must be sure that the next hop has been resolved with the destination MAC address using its app table. So if an app entry does not exist in the app table for the next hop interfaces, it sends an app request. So it will always send an app request because that's the only way. It's like a broadcast, send an app request trying to be sure that it has all the information of the neighboring router. So R2 will then return an app reply with all the information of the destination IP address. So R2 now forwards the packet to R3. As the exit interface is not an interframe network, R2 does not have to resolve the next hop address with the destination MAC address. So here we're saying that when the interface is in the point-to-point, which is like connection between two routers, under a serial connection, the router encapsulates IPv4 packets. And when it does that, what happened that you can forward to the exit interface, or what we call the anchors. So there's no MAC address on serial interface R2. So if you look at where R2 is, R2 set the data link destination address to an equivalent of a broadcast, because you can see there are no MAC addresses on the serial connection. So here you have cable, and here you're looking at serial. So in that case, what does it do? R2 will set data link destination address to an equivalent of broadcast. So you see it more like a broadcast. The R3 will forward the packet to PC2. So recall we have 3 hubs, or from R1 we have 2 hubs with PC2. So R3 now forward the packet to PC2, and that's what happened. So it will always forward it, because remember R2 will learn about R3 when it has exchanged a broadcast in this case, because it's not connected by cable. So if it's connected via a serial connection. So if the entry is not in the app table, R3 will send an app request out of its fast Ethernet connection, just to learn about the IP address of destination device. So you play this video and then see how that works. This video will go a long way to help you how routers choose the best path. It was to how SPF dynamically route to protocol and availability, and then the limitations of static. So that means you don't need manual water limitation. So you need to watch the video. So hubs, bridges, LAN, switches. Network communication devices actually include hubs. When we talk about hubs here, we're talking about legacy, connecting devices, bridges, and LAN switches. So an Ethernet hub acts as a multi-port, a repeater, and receives an incoming electrical signal on the port. And what does it do? It then immediately forward a generated signal out of all ports. So hubs use physical layer processing to forward data. Bridges have two interfaces, because you can see that, and are connected between hubs. So what I do is that the bridges helps to more or less help to strengthen the signal, and then the LAN switches are multiple bridges that connect devices into star topology, which is what most organizations are using currently. Switches also segment a LAN into separate collision domains. So that means you can put them in different virtual LAN or different subnets, as the case may be. So here's the switching operation. Actually, switches use MAC addresses. So every switch you see carries MAC addresses. So when you connect systems to them, remember you use them for distribution oftentimes, they take the MAC addresses of the systems. So what we're saying here is that switches use MAC addresses to direct network communication through the switch in the appropriate port. So by nature, the switch is a broadcast domain, so it broadcasts. So anytime a system connected to switches to send, what happens is that it will send a broadcast, but not to the receiving port, but to every other port. The reason is because it's trying to learn about the other systems. So it gets to get their, through the broadcast, get their MAC addresses and keep them in what we call the CAM table or the MAC table. The following two steps process are performed on every Ethernet frames that enter the switch, and which is one. First, it examines the source MAC address, the source where it is connected to. So most times, if you look at your switch, you often connect to a port, first port, maybe from the router to the switch. So what we're saying here is that examine the source MAC address. Every frame that enters a switch is checked for new MAC address information by examining the frame source MAC address and the port number where the frame entered. So if the source MAC address is not in the table, it adds the MAC address, table along with the incoming port number. So the table. The reason why it's doing this, the next time it will just forward. So if the source MAC address does not exist in the table, what does the switch do? It updates the and refresh timer for that entry. A Unicast address, the switch will look for a match. The switch will always look for a match and the destination MAC address of the frame and entry of its MAC address table. So if the destination MAC address is in the table, what does it do? To forward it out. But if it's not in the table, the switch will forward the frame out all ports except the incoming port. So it has to learn about whether it exists there before it will forward it to it or not. So here's a video of MAC address table we need to watch. And then here is a VLAN like I said, virtual local area network. VLANs provide a way to group devices within a network. So meaning that with VLANs, you can actually create what we call a subdomains like broadcast. If you look at a switch, for instance, the whole switch is a broadcast domain. So if you have more switches on your network, the likely chances you have a congested network is high because there's going to be so much broadcast on such networks. So one of the ways to actually reduce the broadcast nature of the switch is introducing VLANs. So it allows an administrator to segment networks based on factors such as function, project team, or application. So it creates a logical broadcast domain that can span multiple physical LAN segments. It also prevents users of different VLANs, from snooping on each other traffic. So you're going to have 8 VLANs, system connected to that VLAN, will stay in that VLAN, except they are routed to other VLAN. So we have the spanning tree protocol. This is used to actually maintain loop-free path in the layer 2 network at any time. SDP actually has come to help take care of the issue of loop in switches. So loops and duplicate frames have severe consequences on the switch network. So SDP was developed to address those loop issues. Oftentimes, these issues arises, and the only protocol that helps to avoid this loop avoidance is the SDP. So it ensures that there is no logical path between all destinations on the network by blocking redundant paths. So when you have all those paths that are redundant left open, it actually allows for exchange of frames, which leads to what we call loopback issues. And what we're saying here is that it ensures that there's one logical path at every time. And what does it do for you? STBU helps to block free path, what we call redundant path, and ensure that there's some kind of order by passing through a particular port every point in time. So if the path is ever needed to compensate for a network, cable, or switch failure, SDP will have to recalculate the path and unblock the necessary support to allow the redundant path in part 2 what become active. We have configurations for these at the CCNA2 also. So what you need to take away from here is that SDP helps to take care of redundant path. That means if you have so many connections to your different switches, we're saying you have open ports that are free and are connected. We're saying that those open ports can lead to what we call loop problems or loop challenges. But we're saying those loop and duplicate frames that could come up as a result of redundant paths can be blocked using what we call BPDU, which is the Bridge Protocol Data Unit. And that will be used by the SDP to prevent loops. And how does it do that? It blocks certain path and allows certain path to be open, just one path, because if you have several paths open, it could lead to that problem. So lead to what we call loop issues. So multi-layer switching still on the network communication devices. Multi-layer switch actually layer 3. There are switches, call switches, down layer 3, and they perform layer 2 switching and also forward frames based on layer 3. So they have it incorporated. So all Cisco Catalyst multi-layer switches support the following types of layer 3 interfaces: routed port and switch virtual interface. So recall in a multi-layer 3, that's layer 3 switch, every port on that switch is a VLAN. So here is a multi-layer switching. You can see the routed port. So here a routed port is a physical port that acts similarly to an interface on the router. So unlike an access port, a routed port is not associated with a particular VLAN. It behaves like a regular router interface. So also as layer 2 functionality has been removed, layer 2 protocols such as SDP do not function on a routed interface. So some protocols such as the link aggregated function protocol and the internet channel do function at layer 3, unlike Cisco iOS routers routed ports on the on Cisco iOS switch do not support sub interfaces. So what it means is that some of the protocols, such as the link aggregated compression protocol and Etherchannel, they do not function at layer 3. They function more on the layer 2. And then the Cisco iOS routers are actually routed ports on Cisco iOS switch. They do not support sub interfaces. So these are the conditions you must know for multi-layer switching as a route based on its routed port. So those routed ports actually they are physical ports and they act, similar to other router interfaces. And like I said, the switch VLAN interface of a multi-layer switch acts as a VLAN. So you don't need to bother yourself configuring the different ranges of ports in multi-layer switch to cater for VLAN. If you have a multi-layer or a layer 3 switch, you can always do that for such port. So let's quickly look at wireless communication. So you play this, you see this. Remember, before you have any wireless communication, you must have a LAN. That's the reason why we had to look at network communication devices before. Then we'll come down on the communication devices still to look at wireless, because wireless will always sit on your LAN, existing LAN. So wireless versus wired LAN. Wireless LAN use radio frequency, and instead of cables at the physical layer and MAC sublayers. So the IEEE has actually adopted the 802 LAN MAN portfolio of a computer network architecture standard, which includes two dominant working groups. That's the 802.3, which is the Ethernet, and then it has the 802.11, which is the fine Ethernet for wireless LAN. So please note this, that the defined Ethernet, there's an IEEE protocol established that 802.11 is the defined wireless Ethernet. So anytime you're looking at wireless technologies, what comes to your mind is the IEEE 802.11. So wireless also differ from wired, through, which means wireless connect client to the network through a wireless access point. That means wirelessly you're connected. That's what we call wireless LAN. It connects mobile devices wirelessly through the wireless NIC, just like you have a port in your system where you connect cable to, that is wired. But when you connect through the wireless card, inbuilt card, has wireless connection. So here you look at the characteristics of wireless versus wired LAN. The difference between your wireless LAN and your wired LAN is summarized below. For physical layer, for the wireless network, it uses radio frequency. Here physical cable is involved. And then for the media access, the wireless network is actually collision avoidance. And then for 802.3, which is wired, it is collision detection. So this one is what we call the CSMA-CA and the CSMA-CD. So in terms of availability, anyone with a wireless NIC in the range of an access point can connect to it. But when it comes to 802.2 wired network, the physical cable connection is actually required. So significant interfaces is yes. And then when it comes to the Ethernet, it is minimal. And then in terms of regulation, different regulations by country, and then the IEEE standard devices. So the 802.11 frame structure, you can see the frame structure here. So all 802.11 wireless frames contain the following fields. So you can see the frame, the architecture of 802.11. It has a frame control, which actually identifies the type of wireless frame that is contained in the subfield. And then it has a duration, which is like a time range. And then it has an address, which actually contains the MAC address. And then address 2, which is contained the MAC addresses of the transmitting wireless device. So still on the frame structure, you can see the frame structure here. It contains the MAC address, it has a sequence control, it has the address for, and it also has payload. It has the FCS recall. The FCS is the frame check sequence, and the FCS uses the CRC for its analysis, analyze your frame, which is a cyclic redundance check, to check at every point in time if there's some kind of error, between the source and the destination when there's transmission of packet. Okay, so still on wireless, you can't talk about wireless without talking about the CSMA CA and CSMA CE. So wireless LAN are half duplex, the shared media configuration. So why half duplex means that one client can transmit or receive at any given time. Example of half duplex is you're looking at other example when it comes to half duplex transmission is like your walkie-talkie. Walkie-talkie work on a half duplex. You use the same channel to transmit and receive. So shared media means that wireless clients can all transmit and receive on the same radio channel. So this creates a problem because a wireless client cannot hear while it is sending. So which means it's impossible to detect a collision. But in the case of CSMA CD, it will determine and then send it back. So to resolve the problem, wireless now uses what we call the carrier access with collision avoidance as a CSMA CA method to determine how and when to send data on the network. So remember, the half duplex is that it's shared media. In other words, if one client transmits or receives at every given point in time. So a wireless client does the following: listen to the channel to see if it is idle, and then if it's idle, it's sent to send message to the AP, and then to receive clear to send. And then if that is established, if the wireless client does not receive the clear to send, it waits, a random amount of time before sending. So after it receives the CTS, which is clear to send, it now what transmits so that there won't be collision. That's why we say collision avoidance. So here's a wireless client and AP association. So for wireless devices to communicate over a network, they must first associate with an AP or wireless router. You agree with me that for you to have a wireless, to communicate, it has to first associate with a wireless AP. That means it must have a wireless access point. That's why you must be sure that there must be an existing Wi-Fi before you connect with your system. So wireless device completes the following three-stage processes. One, it discovers a wireless AP on its own, and then authenticate with the AP, and then associated with the AP. And that's why you have to be careful for security reasons. Most people just work anyway, see free network, and then connect to it. Those actually allow hackers or threat actors to see everything right there at a glance in your system. In every wireless access point, there are following associations or parameters you must come across. The SSID. SSID is the network name, and then the password, and then you say network mode. This refers to either 11G, 11N, AC, so you have to be careful when you select. Some routers can downgrade, so you can actually select lower. Then the security mode, and then you look at the channel. This refers to the frequency. So you have channels like 1 to 13 in wireless AP. They recall some of them are actually overlapping channels and non-overlapping channels. So like 1, 6, 11 are actually the non-overlapping channels. So we have a passive mode and active discover mode. Remember we said that it will always check through the AP to see if it's available before it to establish connection. And then once the connection is established, then it can send. So there's no connectivity to the wireless network without a wireless AP. So if this mode, the AP openly advertised, and then the primary purpose of the beacon is to allow wireless clients to learn about the network. So we always have the probe and the beacon. The probe in this case would be PC, and the beacon would be at the other end, and then the exchange before information is being transmitted. So still on passive and active discover mode. In this mode, wireless client must know the name of the SID. Remember that I told us why SID is a service set identifier. So the wireless client initiates the process by broadcasting the probe request frame, on multiple channels. It includes the SID name and then the standard support. So always note this, that the active mode may be required if an AP is configured to not broadcast beacon frames. So the active mode will always be there if the beacon is not there. So the beacon is the exchange between your wireless access point. So your system use probe to make requests, while your AP uses what we call the beacon to respond to that request by providing the right IP address. So wireless devices, AP, WAP, and WLC. These are all the different kind of wireless devices we have. So a common wireless design implementation is enabling device to connect wirelessly by LAN. And then in general, a wireless design require wireless access port and clients that have wireless links. So if it doesn't have it, it's not going to connect to it. So home and small businesses uses wireless router. So in small network, the wireless router may be only an access point as well as a small area that requires wireless coverage. So in a larger network, there can be many APs. So you can see different APs in different places. So all the control and management functions of the access point on the network can be actually centralized into a wireless LAN, or what we call a controller. So when using a wireless LAN controller, the APs no longer act actually autonomously, but instead act as a lightweighted APs, and they only forward data between the wireless LAN and the wireless controller. And so here also we have the lightweight APs. They only forward data between the wireless LAN and then they also forward it to they also forward it to your controller, and all management functions such as defining SIDs and authentication are actually conducted on the centralized wireless controller. So a major benefit of centralizing your AP management function in the wireless controller is actually to simplify configuration and help for monitoring. And so in summary, what we're saying here is that your wireless devices can access function as an AP, it can function as a controller, it can also function as a lightweight APs and all that. And this is subject to configuration and monitoring of the various access point. So whichever one you configure it for, it's going to actually work in that direction. So in summary, we've actually looked at end devices, we've looked at router, we've looked at how the behavior of router in terms of its routing table, in terms of its routing information, how it uses certain metrics, to carry out best path selection, to carry out determination of IP forwarding. And then we also looked at switches in terms of receiving one frame and rebroadcasting that frame to other, rebroadcasting that frame. So routers provide better path determination and packet forwarding services. Switches also segmented LAN. A switch makes forwarding decision based on MAC addresses, just like your routers will make decision based on IP addresses. And so we also said here that switches are configured using spanning tree SPT, and the primary aim is to avoid loop, make it a free loop path, and by blocking all redundant paths, so to avoid loop. So multi-layer switches actually are layer 3 switches, and not only perform layer 2 switching, but also forward frames based on layer 3. So if you have a layer 3 switch, what we're saying is that it will act as both to provide you that opportunity to function as a switch and then function as a layer 3. So this is what we have under this topic of network communication devices. So when you look at this in summary, we begin to look at the vulnerabilities, looking at some of the issues associated to wireless network, which of course there are some labs that covers those areas. And then we look at the network devices. And the reason why we're doing this all is because as a cybersecurity analyst, you need to understand how these devices communicate on the network, how they forward the packets, how they use app to resolve between the source and the destination devices, and helping you to mark this whole systems in terms of MAC addresses. So here we've seen the importance of MAC addresses as well as IP addresses. And we've also seen how the ICMP uses ICMP version 6 in case of IPv6, to check for connectivity between two systems. So at this point, I'm going to pause and then give us room to ask questions. So are there questions you would like to ask on this module on network communication? Please, if there's any question, you can raise your hand and I can call your name. If there are no questions, then we look at the next module. Any question? Hello, are we there?
Yes, sir. Yes, sir. We are here, sir. We are here.
Okay, fine. So any question in terms of network communication devices? Do you have any issues with this?
No, everything is good, Doctor. Thank you.
Okay, fine. So for those of us who are new to this, I would advise that you take your time to listen to the recording over and over. Then you can actually, for some folks who, like I said, are new to networking, I've enrolled some of them into CCNA1. And so you could do that as a refresher course. And then while you're listening to this, to catch up with some of the terminology. So I look forward to see that will also help us a lot to be able to move ahead. So we quickly look at network security infrastructure. So I'll introduce that today and then give us the opportunity to walk through what we've done so far. There are questions to ask, you can put them down. And how are labs going? I hope we're doing the labs. Like I said, if you have issues with the labs, you can always post it. Some folks haven't done assessments since we started, not even one module. I don't think it's wise. So please, you have the opportunity still to take your assessment. So it's activated, and you can take it as many times as possible just to help you through. James Porter, I can see you have a question.
Or yes, Doctor. Good evening, Doc. My name is James from Zambia. I wanted to actually just be guided in terms of the labs. Like I'm answering the labs via the weight document. Like I put a question in the answer using the VMs that we've been provided. Am I doing the correct thing? Because I've answered quite a number of labs and they didn't know where to actually submit them to.
Yeah, you can actually answer them directly in the VM and then you screenshot them to show the step-by-step process and like arriving to whatever you're doing. So we just want to see the procedure you took to answer all that. And in some cases, there are questions at the end of each lab which you have to respond to. So your reactions to those questions should be captured, either screenshotted or you type them directly to the lab manual, and then you receive them and then send. Some folks use the lab manual to answer these questions. So they screenshot it and then attach it, make the explanation and move on with it. So you can do both. So you could do directly on the, which of course is better, on the VM, and then screenshot them, then answer your questions. So you save them and then zip them in the folder and then forward to me. I don't think it's different from what you're doing.
All right, thank you very much, Doctor. I appreciate it.
You're welcome. Okay, so any other question? There's no question. But please note you have to take the lab seriously. Okay. So quickly we look. Okay. So let's see. So we're looking at 12, and 12 has to do with network security infrastructure. So I'm going to introduce this module and give us room to reflect on this. And so in the next class, after the labs, we just look at this briefly and then we'll move on from there. So here we've discussed in module 11 about network communicating devices, network devices. And recall we looked at all the different devices you have on the network. Here we'll be looking at network security infrastructure. So if you look at the objective, we should be able to explain network design, influence the network flow or traffic through the network. We should be able to specialize devices that are used to enhance network security, and then how network services enhance network security. So in other words, you're looking at network topologies, looking at security devices, and then you're looking at security services. So let's look at network topologies. Here, this will help a lot those folks who are new using the packet tracer. So you look at a network representation. All this representation you're seeing to your right is a guide to tell you what the end devices are, the intermediary devices on the network, like your switch, your routers, and all that. And then your network media, the different kind of cabling system. So to your left, you can see network interface card, your physical port, and your interface. So the terms port and interface are often used interchangeably. So I need to pause at this point. I want somebody to explain to me, even when they are used interchangeably, there's still a distinction between port and interface. So I may not totally agree with the fact that you use it interchangeably, but you just have to. I need to ask this class now, what is your view about physical ports and interface? Is anyone here who can explain, throw more light to that before I explain it further? Can we hear your own explanation in terms of differentiating between physical ports and interfaces? So when we say network interface, when we say interface on a network, do we mean the same thing? If you think it's the same thing, fine. Do you think sometimes there's a distinction between the two? And under what scenario do you apply this distinction? Anybody? Do you have any? Okay, James, let's hear from you.
Hi, Doc. Well, from my understanding, I feel there is a little bit of a difference, because the physical port cannot be shared, but for interfaces we can even have virtual interfaces. I feel that's my simple answer to it.
Okay, so invariably you're saying the same thing? Hello, James?
Yes, Doc. So I was saying they're actually a bit differ, because in my case, in the way that I'm trying to defend the thing of them differing is because we cannot have a virtual physical port, but rather with interfaces you can actually even have a virtual interface, and you can even aggregate interfaces. So I feel the discrepancy of them being interfaces being able to actually be virtualized and being able to actually, like, you can have multiple of them, yet you can only have one physical interface, is something that makes the two to be a little bit different in my view.
Yeah, excellent. That's my own view too in most cases, because the interface seems to help that takes care of the virtual situation when you're explaining this in terms of multi-parent connections. So you can see like these days where you have the AWS, you have cloud infrastructure and all that. That will help you to explain most of these things. But when you say physical port, everybody wants to see that physical. Of course, still on the virtual situation, you can still say this is a physical port because you're actually looking at it in reality that it exists physically on ground, you can actually access the same port. But the interface helps to generalize this in any of the situations you want to explain it. It helps you to be able to make a very clear explanation. But in terms of physical port, everybody wants to see it physical. So this will be more challenging for upcoming, or do I say new students in the academy, people who are actually very fresh, and it will be very, very confusing. So the interface is fine because you are creating an interface between two systems, you're creating an interface for virtual reality and all that. So it goes a long way to help to explain that better. So of course, in some situations, they are interchangeable. You can still mean the same thing when you say it, but I think the interface gave us room to talk more. Okay, so that's the situation you can see to your right here. And all these are representations we have on the packet tracer, meaning that when we're using the packet tracer for this representation, we should always remember that. And then here on the security infrastructure, we have topologies. These topologies could either be physical or could be logical. If it's physical, is the layout in terms of the way it is being set. You can have a physical topology well arranged in this manner, but of course, some cases the system may not be working, but you have it like a physical layout. And the logical layout is when it is actually having it configured with certain IP addresses, and resources can be shared across that connection. That's logical. It requires some level of configurations or some settings to enable it exchange information. But in the case of the physical topology, in most cases, there might not be exchange of information. You may just have just physical systems connected, but might not be working in some cases, except there's some kind of intervention. And that intervention then enables systems to communicate is what makes it logical. And that's where you have a logical topology. So you can see from the two diagrams, the distinction is there. The one to your right, you can see IP addresses attached to them. And the one to your left, there's no IP address. Please, can you mute your mic, please, if you're not? Hello? Hello? So we have networks of many sizes. So we have a small network, we have small office home networks, as you can see to your right, and then we have the medium, and then we have the worldwide network. So you can see here, under the network topologies, we have LAN, we have WANs. Your LANs have some cases like your intranet, and then you have your wide area network, which could come in as your WAN in this case, and have your public IP addresses in them, and just like you have your private IP addresses in your local LAN. And then here we have a picture to show for what a typical LAN looks like, and then what your WAN is. So you can also see the distinction between the two. Interconnected end devices in a limited area as within a geographical location, and then administered by a single organization. They provide high-speed bandwidth to internal end devices because of the connection. So the kind of cable that is used to connect those devices. But if you look at the WAN, interconnect LANs, across different locations, administered by multiple service providers, as you can see, and then typically provides slower speed links between LANs. Between LANs, you can see the exchange here. So it means you can have a very high throughput here. A high throughput here, when we talk about high throughput in terms of capacity for traffic to be exchanged from one point to the other in terms of their carriage, what they can be able to transmit. So you have maybe a gigabit switch and all that. But when it comes to these connections between these two LAN, there could be some level of limitations here, depending on what is used to connect to different LAN. And so this three-layer network design, we could always, in every network, you have to look at for this. You have the access, which provides endpoints, users direct access to the network. That is where the users actually interface with the access point. And then you have the distribution layer, which aggregate your access layers and provide connectivity to the service. And then you have the core. The core provides connectivity between your distribution layers for large LAN environment. See, this is the hierarchy. You have your core, your distribution, and then you have your access. So you can see here you have some kind of redundancy. You have connections to share in case there's a failure at one point. It can help. So all this, you can see a LAN aggregation here happening here between these two routers. And this is a hierarchical design, if you may ask. So a three-layer network design model, although the hierarchical model has 3 layers. Some smaller enterprise networks may implement a 2-tier hierarchical design. So it depends on which design that matters. So some could use 2 collapsed, one to the other. In this 2-tier hierarchical design, the core and distribution layers are collapsed into 1 layer, thus reducing the cost and complexity. So you can have that 2 together. So like when you have a multi-layer switch, it can help you to collapse that as well. So there's a video for you to play here. So you need to play this video, and with the video you'll be able to view the demonstration of the 3-layer network design model. So common security architectures. Firewall design is actually primarily about the device of interface. It's permitting or denying traffic, based on the source, on the destination, and the type of traffic. So the 3 firewall designs are: 1, we have the public and private, and as it that appears here, the public network or outside network is untrusted, and the private network inside is what is trusted. So you have the public network that's outside, and then you have the private network that is inside, which is trusted. So this is 1, and then 2, the demilitarized zone. In this case, it's still like a switch that you have to configure for this purpose. So a firewall design where there is typically one inside interface connected to the private network, and then outside interface connected to the public network. So you have one to the private, and then you have one to the public. And then you have the DMZ interface, which now connects Hello? Hello, can you hear me?
Sir, you went off for a while, and I think we are back now.
Yeah, I wasn't, and I was like trying to be sure that I'm still connected. So can we hear me now?
Yeah, I think you can hear you. Yes.
Okay, thank you very much. So like we're discussing, we're still talking about the security architecture of a typical network infrastructure. And here we're looking at a DMZ. So you can bring your DMZ between your enterprise network and your ISP. So your DMZ will form a wall between the both sides. And that's why we said inside interface connected to the private network and outside interface connected to the public network. So I could actually use a Cisco Catalyst switch for as a DMZ, making it creating a firewall, some kind of policy within the switch, and then seeing my public connection from the ISP to that switch, and then connecting from that switch to my router. So by the time you bring in some security features in that switch, it's quite that if somebody is trying to get access to your router, the person has to break through that firewall or through that DMZ, which is the demilitarized zone. So it's going to act as some kind of firewall for you in the interim, because like I said, some folks actually connect directly, they just get the connection from the ISP, they plug it straight on their router, and somebody outside your connection can actually get access to your router with ease because that's your router and that's the base of your network. And so it'd be wise to see how you can, first of all, set up a kind of a pre-defense system before having your router. And that's what the military zone does in this case. It comes in between the ISP connection and then your own local network before your main router. And so zone-based policy firewalls, they use the concept of zones to provide additional flexibility. It also uses a group of one or more interfaces that have similar functions or features. The zone also helps to specify where a Cisco IRS firewall rule or policy should be applied. So in this case, this is actually zone-based policy firewalls. So you can see even from the design here, you can see the position here. Here you can see the DMZ. But this DMZ, we're talking about this policy is being applied, and the essence of it is to provide additional, some kind of flexibility to the network. But all this is to help stall activities between the ingress and outgress of the network. So it doesn't have direct, it doesn't give anybody direct access to your network. The essence of this also is not to allow the threat actors to have direct access to your LAN network. So there's a packet tracer activity here, which will you will observe the following: packet flow in LAN in one topology, and then change in packet flow path when there is a change in the network topology. So I advise you walk through them, and then let's look at the security devices. You need to watch this video. It will help cover the following: workgroup switches to provide port security, and then help you for dynamic app inspection, DHCP snooping, and then looking at multi-layer multi-layers in terms of there are 4 firewalls, and then it also helps wireless access point, web, email, SSL, proxy firewalls, intrusion detection. So we need to watch the video to learn more. And then still on firewalls, a firewall, what is a firewall? It's a system. It's actually a group of systems that enforces an access control policy between networks. So firewalls is a defensive mechanism that enables to, it helps to create policies, common firewall properties. Example, resistant to network attacks, to the only transmit point between internal corporate networks and external network, because all traffic flows through the firewall. It enforces the access control policies. And we need to play this to see what the firewall does. Like we said, it helps to do what control the inbound and outbound. You can also use it to do permit and deny, all bounds, through in and out. These are regulations. You can come up with some kind of control policies. And still, there are benefits and limitations of firewalls. Can we just see some of them? In the firewall benefits, it prevents the exposure of sensitive hosts, resources, and applications to trusted users. It also helps to sanitize protocol flow and prevent the exploitations of protocol flaws. It blocks malicious data from servers and client. And then it reduces security and management complexity. So you can see the reason why you should go for one in your organization, why you should have a firewall to be able to help you filter all this. And firewall limitations. A misconfigured firewall can have several consequences, for sure, because you bring it in between. So if it's not well configured, it can also lead to a single point of failure, on your network, thereby not making your network available. Remember, your network ought to be available at every point in time. And then the data from many applications cannot, passed over firewalls securely. Users might proactively search for ways around the firewalls to receive blocked material, which exposes the network to potential attack. Network performance can slow down if it's not properly configured. Unauthorized traffic can be tunneled or hidden as legitimate traffic through the file. So there are limitations, actually, because of the too much policies that's being added. So you can see a lot of filtering processes going on. So we're saying that there are some likely limitations if it is not properly handled. So different types of firewalls are packet filtering. So packet filtering is also seen as stateless firewall. The packet filtering firewalls are part of a router firewall incorporated, which permits or denies traffic based on layer 3 and layer 4 information. And most of us who've done some kind of access list control will see that a lot of restrictions. So you're looking at how to permit denying traffic in terms of IP addresses and the port numbers. They are stateless firewalls that use simple policy table lookup that filter traffic based on specific criteria. Okay, so the criteria could be IP address, it could be filter for based on port. So stateless firewalls are the most versatile and the most common firewall technologies in use. This firewall provides stateful packets filtering by using connection information maintained in a state table. Okay, so we have application gateway firewall. Application gateway firewall filters information at the layer 3. So what is layer 3? That's the IP layer 4, transport 5, section 7 of the OSI model. So most of the firewall control and filtering is done in the software. So this is more of services running on applications. So we also have the next generation firewalls. So as you can see to your right, go beyond stateful firewalls. It provides integrated intrusion prevention, application awareness and control to use the block risky apps. It also upgrades parts to include future information feeds, techniques to address evolving security threats. So these are next generation firewalls. You can use them to be able to create some kind of filter for your inbound and outbound traffic. And firewall type descriptions to continue. Other methods of implementing firewalls include host-based, which is server and personal firewall, transparent firewall, and hybrid firewall. So the intrusion prevention and detection devices. So here you have a networking architecture paradigm shift, which is required to define against fast-moving evolving attacks. So we're saying that the most include cost-effective and prevention system could be intrusion detection and intrusion prevention system. So the network architecture integrates these solutions into entry and exit point on the network, and so that you can be able to monitor in and out traffic. We have a couple of labs, associated to the intrusion detection and that of the prevention systems. So all that we're going to do in the labs. And so advantage and disadvantage of the IDS. One, for the IDS, no impact on network. No network impact if there's a sensor failure. No network impact if there's sensor overload. And for the IPS, it stops trigger packets and can use streamed normalization techniques. The disadvantage of IDS is that the response actions can stop trigger a packet, and then it can correct tuning with required response action. So more vulnerable to network security evasion techniques. But in terms of the IPS, which is more reliable, the sensors issues might affect network traffic in some cases, and sensors overlapping, but you can see to stop trigger packets and can use stream normalization techniques. So IPS and IDS technologies can implement each other, complement each other. That means you can use both. And then deciding which implementation to use is based on the security goals of your organization, as well as stated in their network security policy. Remember, every organization ought to have its own network policy. So there are two primary kinds of IPS. One, host-based, and two, network-based. So for the host-based IPS, it's a software installed on host to monitor and analyze suspicious activity. So advantage is that to provide protection specific to host operating system, and it also provide operating system and application level protection, and then to provide the host after the message is what decrypted. So this is actually installed in a host device, while the network has to be on the network. So network-based intrusion prevention systems are implemented using a dedicated or non-dedicated IPS device. Host-based IPS solutions are integrated with a network-based IPS implementation to ensure a robust security architecture. So you can see the sensor in between. You can see in this case, this is within the network itself. For the IPS, that's the intrusion prevention system. The sensors detect malicious and unauthorized activity in real time and can take action when necessary. So few examples of socialized security appliances. One is this Cisco Advanced Malware Protection. This is actually an enterprise class advanced malware analysis and protection solution. It provides comprehensive malware protection for organizations before and during and after their attack. And we also have the Cisco Web Security Appliance. We also have the Cisco Email Security Appliance. This example of specialized security appliances that are available. Cisco has this, and what we do to help protect and block risk, sites, test unknown sites, and also help users to be able to solve freely, making sure they block malwares and all that. So these are actually available. So let's look at security devices, some of security services. Traffic control with access list control. Access list control also will be done as a lab, also in this course. Also in CCNE, you'll have come across access list control. Those of us that are instructors here will agree that a number of labs have to be done on the access list control. So this is also part of some kind of security policies that will help under security services. So to assess access list, It's a series of commands that control whether a device forwards or drops a packet based on information found in the packet header. So the packet header will tell based on what it has been asked to do, either to deny or permit. So you can actually deny certain services, you can deny certain IP or network or port to be able to access certain kind of activity. So when configure access list perform the following tasks, so these are the tasks that access list will help you achieve in terms of security on your network. One, it will limit network traffic to increase network performance. Yes, because you're going to deny one or two net systems or networks not to access one or two resources. So definitely to increase the network performance, because traffic, remember, traffic leads to congestion. Traffic leads to high bandwidth utilization. And so with that, you'll be able to have some kind of high speed here. It provides traffic flow control, provide a basic level of security for network access, and filter traffic based on traffic type. It also screen hosts to permit or deny access to network services. So access list important features. There are two of them, basically on that IPv4. It could be standard, it could be extended. You know, for the standard, it's used to permit only and deny traffic from source IPv4 address, and your extended access list filters IPv4 packets based on several attributes, which includes your protocol type. So you can see that the standard only is to deny traffic only from the source IPv4, but your extended to help you achieve protocol type, source IPv4 address, the destination, the source TCP UDP, the destination TCP or UDP. So you can note the number of ports that are associated to TCP UDP. You can actually block some of those ports. Optional protocol type information for finder control. The standard and external access list control can be created using either a number or name to identify the access list and its list of statements. So for those who are new to access list, if you go through this is CCNA2, you could see a number of configurations. But the good thing about this in this course now is that we're looking at it in terms of the applications directly. So once you're able to do that, be fine. So we have a packet tracer activity for that. So in the lab, you'll be able to how an access list can be used to prevent a ping from reaching hosts on remote networks. After removing the access list from the configuration, the pings will be successful. So meaning that when you prevent certain system because you have blocked them, when you remove it, you see that they can be able to connect. So security services still, we have a simple network management protocol. It's actually an application layer protocol that provides a message format for communication between managers and clients. So it allows the network administrator to perform the following. One, what does it do? It manages end devices such as your servers, your workstations, your routers, your switches, your security appliances on an IP network. It also helps you to monitor and manage network performance. It helps you to find and solve network problems. It's a plan for network growth. The SMP or systems consists of two elements. One, the SMP manager, which runs SMP management software. The SMP agent nodes are being monitored and managed. Remember, this SMP is very, very good. It's an application that provides a message format. It gives you all the message format to help you monitor your servers, your traffics. It gives you an insight of the activities that's happening on your network and helps you to show your performance, your utilization, so whether you're actually utilizing it optimally or not. I mean, it's quite a very good tool to be used as a network administrator. If you don't have it, then you're losing a lot because it helps you to do a lot of interpretations on your network. And it also helps you solve some network problems. It's planned for network growth. It also helps the network scale because you can see so much activities. You can see so much downtimes, issues associated to your network. So I advise that if you don't have that on your network, you should get one. And then we have NetFlow. NetFlow is a Cisco iOS technology that provides statistics on packets flowing through a Cisco router or multi-layer switch. The NetFlow actually provides data to enable network security monitoring. It also helps with network planning. It helps with traffic analysis to increase identification of network bottlenecks, issues, some kind of limitations on the network. It also helps for IP accounting for billing purposes. And NetFlow can monitor applications, connection, track bytes and packet count for that individual application flow. It then pushes statistics over an external server called the NetFlow collector. So you can see the role it plays there. So it gives you that statistical view on packet. It's showing you through the different the packet's behavior. So probably the certain applications or certain services that are actually taking up more of your bandwidth, all that you see there in the distribution. And so we have port mirroring. It's actually a feature that allows a switch to make a duplicate copies of traffic passing through a switch and then send output with a network monitor attached. So we have a 6-log service. This is actually the most common method of accessing system messages. Is to use a protocol called 6-log. So the 6-log protocol allows networking devices to send their system messages across the network to 6-log servers. It provides 3 primary functions. What are they? One, the ability to gather login information for monitoring and troubleshooting. So you can gather a lot of login information to see challenges, issues, severity of some of the problems you might be having, and then troubleshooting. It also helps to select the type of login information that is captured, and then the ability to help you specify the distinction of captured 6-log messages. Remember, the 6-log messages helps you to actually assess. It also helps you to gather so many information about your networks and know issues associated with it, and also helps in troubleshooting to resolve some of the challenges and issues you might be having on the network. So you have the NTP, which is also a very good one. It is important to synchronize the network across all devices on the network. The date and time settings on a network device can be set using one or two of the methods. It has a manual configuration of the date and time, configuring the network time protocol. The NTP networks use a hierarchical system of time, such where each level in this system is called a stratum. NTP servers are managed in these 3 levels known as strata, which is 0, for instance, and NTP network gets the time from authoritative time source, which is at stratum 0. When it's 1, the device are actually directly connected to the authoritative time source. Remember, when you go to time source, we're looking at the source here. You can see the time from the diagram here. You can see that. And then when it's 2 and lower stratum 2 devices such as the NTP client will synchronize their timing using the NTP packet from stratum 1 servers. And all this is just to help you monitor the date and time settings in the network and set one of 2 methods. So it goes a long way to help in terms of server management, and then helps you to monitor the timing on the networks, and then also help you to arrange help to synchronize and keep your network in high performance in terms of synchronization. So to help you synchronize all these activities for better management. And then we have the AA servers. The below table lists the 3 important independent security functions actually provided by the AAA architecture. And when we talk about the AA, I actually mentioned this earlier. is one for authentications. When you talk about authentications, you're looking at users and visitor must prove that they are who they are. Those who must connect most authentication. Authentication can be established using username and password. So these are functions of the AA servers. The servers provide this because to be able to help you manage your network effectively. So one is authenticated, somebody must authorize that authentication. So after the user is authenticated, authorization must be granted. And an example is user student can access host server XYZ using SSH. There's a secure shell on port 22. Then accounting is accounting records. The user shows who and who connected, what kind of resources was accessed, and then how long the amount of time that was taken actually formed your accounting. All that you can capture in the server. And still on the functionality, the standard transport. When you talk about the transport, you're talking about TCP, the UDP, and then you talk about the protocol CHAP, which is bidirectional challenge and responses, or response as used in challenge handshake authentication protocol, which is the CHAP. And then the functionality, which is the entire packet encrypted, and then we have the customization, which provide authorization of routers, commands per users or per group. And then we have the accounting limited. So for the tax, we're looking at all these as part of the AAA services. So these are actually lists and difference between the terminal access controller system and then your remote authentication dial in user services. So you can see the difference between the two in terms of the behavior of the AA service. Remember, your AA service for authentication. Remember, it also helps you to account. And then, so your authentication, authorization, and accounting. These functions you must always remember when it comes to the behavior of your AA server. And looking at VPN, is actually a private network. You can see this occur within the internet. So it's like having a layer through the internet for some high level protection. So when two organizations want to establish secure connection, sometimes they might be far apart through some geographic, maybe widely set apart, but through VPN, they can use the same internet to provide some secure connection. So the VPN, which is a virtual private network, is created over a public network. It uses virtual connection routed through the internet from the organization to a remote site. Your VPN is a communications environment to which access is strictly controlled to permit peer connections with a defined community of interest. So you can have community of interest coming together to collaborate and using the connection. So you can see for a normal VPN, you have a private network at the two ends, but this actually connected through some kind of public connection. So your individual private net IPs are still needed, but the configuration now will be done between the two public network across the network. So confidentiality is achieved by encrypting the traffic. So the traffic between these two organizational two systems actually is encrypted. So in short, VPN connects to endpoints over a public network, as you can see, to perform or to form a logical connection, which can be made at layer 2 or layer 3. And so that's all the network security infrastructure. And in summary, as a takeaway is that the network are typically represented as physical or top logical. Logical is when it's configured, and then we looked at the physical topology, how it is being presented, and we also looked at logical topology, how it is configured, and the two most common type of network infrastructure, LAN WANs, and the campus wired network. We look at the hierarchical layers, how networks are arranged, They are arranged from core distribution access. In some cases, you have it collapsed where you have your distributional core as one. And I said your layer 3 switch can actually function as that. I mean, you can see layer switch taking care of your core and your distribution. So the different types of firewalls are packet filtering firewalls, stateful inspection firewall, application gateway firewalls, and next generation firewalls. And so the intrusion prevention system is also there. We have specialized security appliances that are available. And then we also talked about the access list control. We talked about the simple network monitoring protocol. We also talked about the net flow, talk about the port mirroring. This essentially is what we discussed under the network security infrastructure. We talked about 6log, the NTP, talked about the AAA service, and then we talked about the VPN. The good thing about it is that there are practical labs that will help us understand this better as we dive into some of the hands-on. And new terms that you will have come across, the course also stated here. So that brings us to the end of this module. And like I said, tomorrow we'll look at some of the labs that might be of some concern to some of us. Then we'll move on. So is there any questions? We can react to those questions. Any question? Actually, this is 6:30, so if there are questions, we can just look at those questions. Any question? But please try as much as possible to send in your labs. Like I said, if you have concern issues with any of the labs, you can send. I see neither having issues with the lab, which we'll discuss that tomorrow. We'll work on that lab together and share experience and see what that could be. So, but I know too well that when you're going to do some of these labs, one, be sure that your internet is working. Check to see that your Firefox can browse. Check to see if there's connectivity at every stage so that you don't end up looking out for information that will be difficult for you to fetch. Is there any question? I can see somebody raising his hand.
Doctor, for the lab 938 on step 3.
Okay, you can just send it to me, or you can post it to the WhatsApp group. Are you on the group with us, Jamila?
Yes.
Oh, please do, so we can address those labs tomorrow.
Okay.
Yeah, sure. So I just want to keep to the time, so those of us that will have to go for prayers can prepare for that. So if there are other questions, you can send them. So I'm going to be looking at 9.3, 9.2, that's for 9.2.6. So we just work on those labs. And then please keep sending your labs and keep doing your assessment. For those of you that have not done anything in your assessment, you have to do. Not when we're closing off this training, you're struggling to do your assessment. I don't think it's the best. So it will be nice you start catching up from now. So by the end of this week, we have more labs to do. So it's best you've done the earlier ones so that you don't have so much labs trapped. Okay, so thank you very much for your time. And like I said, we'll see you tomorrow virtually for some of the labs, and then we'll move on with the other parts of the modules. So the assessments are all activated, and my email is on the group chat. I'm going to send it again. So those of you who probably have lost track of the email, so that whatever you're able to, whatever labs you've covered, you can send it directly to me for your assessment. So thank you all, and good night from here. Good night, everyone.